Hello, and welcome back. In this video, we will have our final epic battle of the trilogy. We will need everything in our power to defeat this rational function in example 2. May the forks be with us. First, let's look at the domain of the function. Let me put my fork away. So for the domain of this function, we want to think about all the x values that we could possibly plug into it, which is everything except for -1. So one way of writing that would be an interval notation. All the numbers from -infinity to -1 and then -1 to infinity. But you can also write it as just all real numbers except for -1, or however you like to write this domain. So the second thing will be to find the x-intercepts. Again, remember, to find the x-intercepts, you set y equal to 0. Or in other words, set your function equal to 0. But as we were saying in some of the previous packets of the trilogy, the only way a fraction can be 0 is if the top of the fraction is 0. So we can just write the top of the fraction equals 0. That makes sense because if you do set the whole fraction equal to 0, the very next step you can always take is to multiply both sides of the equation through by the denominator of the fraction. And that'll get rid of the denominator and give you with an equation the top equals 0. So we get x equals 0, which corresponds with an x-intercept of 0, 0. Now if we have an x-intercept of 0, 0, we know that we're going to have a y-intercept of 0, 0. And if it's a function, then that's going to be the only y-intercept. Let's go ahead and just go through the motions of finding the y-intercept anyway. Here we plug in 0 into the function to find the y-intercept, and we get 0 as expected. Step 3 will be to find vertical and horizontal asymptotes. So first we'll look at vertical asymptotes, see if there are any. And here we have a rational function. So we can think the vertical asymptote will happen when the bottom of the function is equal to 0. Which is at x equals -1, and where the top is not equal to 0. So note the top is not equal to 0 at x equals -1. So there's a vertical asymptote, x equals -1. Let's look at horizontal asymptotes. The funnier of the two asymptotes. Ha ha ha. So the horizontal asymptotes for rational functions are going to happen, or we're going to look at the degrees to determine them. So let's go ahead and expand out the denominator. We have x squared plus 2x plus 1, just so that we can look at the degree of the bottom. It's a 2, degree 2 on the bottom. Degree 1 on the top, so since the top degree is less than the bottom degree, we'll have a horizontal asymptote y equals 0. That was one of the heuristics for rational functions. So we can say, since the degree of the top is less than the degree of the bottom, we have a horizontal asymptote y equal 0. Actually, I don't need to box these. There. Okay, so step 4 will be to find the first derivative. Now for the first derivative, we've got a quotient, so we're going to be using the quotient rule. Low d high minus high d low. Oops. Over low squared. There we go. Now, talking through that, we have the low d high, the derivative of x is 1, minus high, which is x, d low. So I took the derivative from the x plus 1 squared. There, it involved a chain rule. Derivative of outer function was multiplying the 2 in front and subtracting 1 from the exponent. That's where I got the 2 times x plus 1. And then we have to multiply by the derivative of the inside, which is 1. Now, if you know that it's a times 1, you don't have to write that. Times 1 doesn't do anything. All I'm doing is writing it here for emphasis, but you don't have to write that when you're doing the work. Now let's take a moment to clean this up. On the bottom, we'll have the x plus 1 to the 4th. Now there's an x plus 1 factor in each of these terms on the top. So we can factor out that x plus 1 factor, and we're left with, well, just x plus 1 from the first term, and then 2x from the second term. On the bottom, we still have x plus 1 to the 4th. But now that the top is factored, we can cancel a factor of x plus 1. And then simplify on the top, and we get 1 minus x over x plus 1 to the 3rd. That's to the 3rd. Okay, so that's the first derivative. Let's figure out where the first derivative is equal to 0 and where the first derivative does not exist. Well, here I'm going to jump in and say the first derivative is equal to 0 when the top of that fraction is equal to 0. When 1 minus x is equal to 0, which happens at x equals 1. And the first derivative does not exist when the bottom of the fraction is equal to 0, which happens at x equals negative 1. Now let's turn to the second derivative. Second derivative is going to involve another quotient rule. Low d high minus high d low. Over low squared. John Williams wrote that. Just kidding. Okay. So here we have a common x plus 1 squared that we can pull out from both the first term and the second term, even before we simplify. Let's go ahead and do that right away. X plus 1 squared, there's going to be an x plus 1 left over from the first term along with a negative 1 factor. And we have minus 1 minus x times 3, and that's it from the second term. And on the bottom, we've got x plus 1 to the 3 times 2, which is 6. Now, on the top, if we distribute, we'll get negative x minus 1. And here you'll get 3 minus 3x. If you combine those together, you'll have negative x minus negative 3x, which is negative x plus 3x, which is 2x. So on the top, we're going to get 2x. And then for the constant part, we're going to have negative 1 minus 3, which is negative 4. Okay. And if we wanted to, we could write the factored version of the top as well, just for reference. 2 times x minus 2. We can keep that in our back pocket in case we needed it. Whoop, wrong color. So there are the first and second derivatives. Now we're going to put those together in a sign analysis chart. Here we're going to throw in all the x values that we found. Whoops, I forgot. We didn't find any x values for the second derivative. Well, everybody makes mistakes. But not everyone records them. So first we have to find where the second derivative is 0 and dne. Well, the second derivative is going to be 0 when the top is 0, which happens at x equals 2, it looks like, and dne when the bottom is 0, which happens at x equals negative 1. Whew, we almost lost the battle. That was a close one. So now we're going to put in all the x values that we found, this time we found them, up on a number line. Just make sure they're in order. They don't have to be exactly to scale, but as long as they're in order from smallest to biggest, that's the only thing that matters. Now we're going to make a row for the first and second derivatives. We're going to collect all the places that we found where they were 0 and d and e. So, for example, the first derivative is equal to 0 at x equals 1. 0 at x equals 1. First derivative was d and e at x equals negative 1. So we'll put that there. Remember that this row is the row that represents the outputs of the first derivative if you plug in these x values. So if you plug in the x value of 1, the first derivative is 0. If you plug in the x value of negative 1, the first derivative just doesn't exist. Now for the second derivative, that's equal to 0 when x is equal to 2. And the second derivative is d and e when x is equal to negative 1. And these are the markers for where you might be changing signs. So it's helpful to put these up first so that you know where you're going to have to test to see if you change signs as you cross those x values. So let's start off with the first derivative on that first interval with x less than negative 1. So maybe like negative 2, for example. If we plug that into the first derivative that we got, negative 2 will make the top positive, and then negative 2 plus 1, that's negative 1 to the third, that makes the bottom negative. So overall, we're going to have a negative sign for the first derivative. Now when we cross negative 1, is the sign going to flip? Yes, because the corresponding x plus 1 factor has an odd exponent. So the sign will flip. As we cross x equals 1, will the sign flip? Yes, because the corresponding factor 1 minus x has an odd exponent, and so the sign will flip. And that sign will stay negative at 2 and after 2, from 1 all the way to infinity. It'll stay negative. Let me erase my little sign there. Okay. Now we can move on to the second derivative. First, we'll get a starting sign. So here we have negative 2 again, we can plug in, and on the top, if we plug in negative 2, we're going to get a negative minus 4, that's a negative on the top. If we plug in negative 2 on the bottom, anything to the fourth power will be positive. So second derivative also starts off negative. Is the sign going to flip as you cross negative 1? No, because the x plus 1 factor has an even exponent. So it'll stay negative as you cross negative 1. And it's going to stay negative until you bump up against either a 0 or a d and e, in which case you have to check again. Does the sign flip? So does the sign flip as we cross x equals 2? Yes, because that factor, the 2x minus 4, or you can think of the factored version, the x minus 2, that's going to flip the sign because it has an odd exponent. Basically what's happening is that factor flips to a positive when you plug in an x value that's bigger than 2. And a positive divided by a positive is positive. Okay, so we have our sign analysis for the first and second derivatives. Let's get a little practice drawing the pieces of the graph before we go to the coordinate system. What can you say about the first interval from negative infinity to negative 1? What's happening to the graph? So if you said the graph is decreasing and concave down, then that would be correct. First derivative negative means decreasing. Second derivative negative means concave down. So the decreasing part we can write like this. If a dot starts up here, then if you move to the right, the dot will be lower because it's decreasing. And then concave down means part of a frown. So this is going to be the right side of the frown. What's happening on the second interval? If you said increasing and concave down, then that's correct. So here we're going to be increasing, going up as you go to the right, and part of a frown, concave down, part of a frown. In this case, the left half of the frown, right? We have both sides of the frown. what about as x goes from 1 to 2? What is the first and the second derivative telling you there? If you said decreasing and concave down, then that's correct. So again, decreasing and concave down, part of a frown. And the last interval, if you said decreasing and concave up, that's correct. Decreasing, so going down as you go to the right, and concave up, part of a cup. This is the left half of the cup. So now we know the little pieces of what our graph looks like, the behavior of the graph. Let's take one last step before we come to the coordinate system. And that step is to find any kind of maxes or mins or inflection points. So looking for maxes and mins, we're going to look to see where the first derivative changes signs. So here it's going to change from negative to positive. Looks like we might have a min there at -1. In fact, it kind of goes down and then goes back up, so maybe we have a min there. But if you plug in -1 into the function to try to get the y value of that minimum point there, you're going to get undefined. If you plug back into the original function, -1 plus 1 is 0, and then you have -1 over 0, which is undefined. So there really isn't any point on the graph there at -1, so there can't be a minimum value there. In fact, we even found earlier that there was a horizontal or vertical asymptote there. So we can even draw that in our picture if we want to. So no min there. Now there's another change of sign as we cross x equals 1. We're going from positive to negative, so increasing to decreasing. We can see it right there. There's going to be a max happening there at x equals 1. So the max is at 1 comma whatever f of 1 is. In this case, it looks like it's going to be 1/4 if you plug 1 into the original function. Remember that to get this, you plug 1 into the original function. Now there aren't any other sign changes for f prime. So there aren't any other maxes or mins. Oh, before we leave the maxes and mins though, just to talk about the second derivative test, because we've been using the first derivative test looking for sign changes of the first derivative. We can also think about this max that we found as coming from the second derivative test. X equals 1 is a place where f prime is equal to 0. And then if we plug x equals 1 into the second derivative, we get a negative value. Negative meaning concave down, like a frown. And there at the top of the frown is where your max is. So you can use the second derivative test looking at this column, or you can look at the row and think about the first derivative test. Mostly you'll be thinking about the first derivative test. I just wanted to point out that you can also read other things out of this sign analysis chart that we've made. Now for the second derivative, it only changes signs at one x value, and that's here at x equals 2. It goes from negative to positive, concave down to concave up. So that change in concavity is happening at an inflection point, IP. Not intellectual property or internet protocol, inflection point. So that's going to be at 2 comma f of 2, which ends up being 2/9. And that's all we have for maxes, mins, and inflection points. So we didn't actually have a minimum value, looks like. Let's take all of this stuff and put it on the coordinate system. We have our x and y intercept at 0, 0. We have our vertical asymptote, x equals -1. We have our horizontal asymptote, y equals 0. And we have our max 1 comma 1/4. I draw that a little bit higher than maybe a fourth, just to help with drawing the picture. And then 2 comma 2/9. I'll draw that maybe like right here. Now we're going to piece together the graph. So on the first interval from -∞ to -1, the graph starts close to the horizontal asymptote first off. If you're out here at -∞, you're really close to the horizontal asymptote. One thing that I probably didn't mention is that with rational functions, you're only going to have at most one horizontal asymptote. And if there is a horizontal asymptote like we have here, then it's going to, the graph will approach that horizontal asymptote in both directions. So as x goes to positive infinity and as x goes to negative infinity, the graph will get closer and closer to that horizontal asymptote. So that means that if we're here at an x value that's towards negative infinity, you're going to be very close to the horizontal asymptote. Then as we move to the right, we're going to be decreasing and concave down. And as we get closer to x equals -1, closer to that vertical asymptote, we're going to be falling and getting closer to that vertical asymptote. So the graph will look something like this. Something like that. So going to the left, the graph gets closer to the horizontal asymptote. Going to the right, the graph is getting, falling down and getting closer to this vertical asymptote. Let's look at what happens on the other side of the vertical asymptote. So from -1 to 1, it looks like the graph is increasing and concave down. Now, right on the other side of -1, we're going to be close to that vertical asymptote. So we're going to start down very low here, and then come up, go through this point at 0, 0, and then head into this 1, 1/4 point, which is where we have the max. It's going to look something like this. And we had to be concave down through this process. Now sometimes it's a little hard to get exactly concave down. The curve might end up looking a little straight. Just try to make it as much concave down as possible throughout this whole interval. So there it is. Now the interval from 1 to 2, it looks like the graph is decreasing and concave down. So from this point to this point, the graph is decreasing and concave down. Again, a little bit hard to show the concavity there because the y values are so close to each other. Just try to show it as best as you can. And then from the interval from 2 to infinity, the graph is decreasing and concave up and getting closer to that horizontal asymptote as we go to the right. So it looks something like this. Whew, that was quite a battle, but in the end, we won. We graphed the rational function. Thanks so much for watching, and I'll see you next time.